All right, let's do this. Welcome to a super high-speed crash course on the fundamentals of computer architecture. Seriously, if you're studying for an exam or you just want to finally get what's going on inside your computer, you are in the right place. We're about to pack a whole semester into the next few minutes.
So, I want you to think of this as the ultimate cram session, okay? We're covering the absolute essentials, everything you need to know, all boiled down into one rapid-fire explainer. No fluff, just the core stuff. So, let's get right into it.
So, here's our syllabus for today. First, we're going to separate the blueprint from the actual build. Then, we'll look at the core components, the parts every computer has to have. After that, we're going to dissect the brain itself, the CPU. And we'll wrap it all up with a lightning round on the history that got us to where we are today. Okay, Section 1. Before we can even touch the hardware, you've got to understand two of the most fundamental ideas in all of computing. And listen up, because this is a classic exam question, so you're going to want to know this.
So here's the deal. Architecture is the what. It's the blueprint, right? It's what the programmer sees and interacts with. Organization is the how. That's the actual hardware, the physical stuff that makes the blueprint work. Think of it like this. An architect draws the plans for a house. That's the architecture. But the construction crew deciding to use steel beams instead of wood, that's the organization. One is the plan, the other is how you actually build it.
And you know what? No matter how fancy or how simple, every single computer boils down to just these four jobs. It has to process data, it has to store data, it has to move data around, and it needs a control unit to orchestrate the whole show. That's it. Get these four things right, and you've got yourself a computer.
All right, so we've covered the big ideas. Now let's talk about the actual hardware. What are the main structural parts that make up a computer? This is the basic anatomy lesson.
First up, the absolute star of the show, the CPU, the central processing unit. This is without a doubt the brain of the whole operation. It is the master controller. It fetches instructions, it does the math. Literally everything your computer does is because the CPU told it to.
But a brain is pretty useless without a notepad, right? That's main memory. Think of it as the CPU's short-term workspace. It's where all the data and instructions it needs right now are kept. And here's the key term. It's volatile, which is just a fancy way of saying when you kill the power, poof, everything in it is gone.
Next up is input/output, or just I/O. Super simple concept. This is just how the computer talks to the outside world and how we talk back to it. Your keyboard, your monitor, your mouse, all of that stuff is part of the I/O system. It's the bridge between us and the machine.
So how do all these different parts talk to one another? Well, they all get on the system bus. It's basically a communication superhighway, a whole bunch of electrical pathways that connect the CPU, the memory, and the I/O, letting them all exchange data. Without the bus, you just have a box full of very expensive, very disconnected parts.
Okay, Section 3. We've seen the big pieces on the motherboard. Now it's time to zoom way in. We're going inside the brain itself. We're going to take a look at what a modern CPU is actually made of.
And the first thing you'll find inside a modern CPU isn't just one brain. It's several. We call these cores. And each core is its own independent processing unit. This is the magic behind multitasking. Having multiple cores is like having multiple brains working on different problems at the exact same time.
Now, to work as fast as possible, the CPU has this brilliant system called a memory hierarchy. Look at this. The data it needs right now, this very microsecond, is in the registers, the fastest possible storage built right into the core. Then you have these tiny ultra-fast caches, L1 and L2, for data it's probably going to need soon. And finally, there's a bigger shared L3 cache for everyone. The whole idea is to keep the most important data as physically close to the brain as possible.
And that brings us to our final section. We know how computers work today, but how on earth did we get here? This is your history lesson in hyperspeed, a quick trip through time to see how we went from room-sized calculators to the devices we have today.
It's honestly amazing. In just a few decades, we've blasted through 6 generations of computing. We started with these huge hot vacuum tubes back in the 40s. Then came the transistor, which changed everything. From there, it just became a race to shrink things down, to cram more and more components onto a single chip, until we get to today, where we can fit billions of them in a space smaller than your fingernail.
And I really want to stop for a second on the transistor, because it was a total game changer. I mean, just look at this. Compared to the vacuum tube, It was tiny, it ran cool, it was way cheaper, and it was 5 times faster. This one little invention is the reason computers went from being government-owned, room-sized behemoths to something you can carry in your pocket.
And you know, this incredible shrinking act wasn't random. It followed this weirdly predictable pace, which was famously pointed out by Intel's co-founder Gordon Moore. His observation, which we now call Moore's Law, basically became the golden rule for the entire tech industry.
2x. That's the magic number. This idea that the power of a computer chip would essentially double every year and a half for the same price, that's the engine that has driven our digital world for more than 50 years. It's not a law of physics, but it was an incredible observation about the pace of human ingenuity.
And the results of that relentless doubling? Well, they're all around us. Because of Moore's Law, our computers got exponentially cheaper, faster, and smaller, all while their memory just exploded. I mean, think about it. The internet, smartphones, AI, none of it would be possible if this trend hadn't held true for decades.
And that brings us to the end of our cram session, with one last, really big question. For over 50 years, Moore's Law has defined our world. But now, we are pushing up against the absolute limits of physics. We literally can't shrink transistors much more. So the question we're all wrestling with is, what happens when the law finally breaks? What does the next generation of computing even look like? Well, that's the final exam for the engineers of tomorrow. Thanks for watching.